Welcome to the UGC lecture series. In this lecture, we are going to talk about binary search trees. We are just going to have a small recap of what is meant by a binary search tree. Then we are going to look at how to search a binary search tree and do insertion on binary search trees. In fact, when we are doing insertion, we also have to search for a place in which to insert. So, that also involves search. This is what we are going to see in this lecture. So, that is we are going to have a recap of the binary search tree. We are going to search a binary search tree and then we are going to do insertion into a binary search tree. So, just to recap on what is a binary search tree. A binary tree is called a binary search tree if each node n, the value at n is greater than every value in the left subtree and is less than every value in the right subtree of n. So, let us first look at searching a binary search tree. Given such a tree, now this is a typical tree that we would see in a real application of binary search tree, like for example databases. Databases uses some form of binary search tree, not exactly this, but this is a basic form. And unusually, like how we normally have only A, B, C, D or 1, 2, 3 for simple data in the nodes, in this particular example we are having quite a large key values. This is actually real applications. And there is another condition that we put on a binary search tree, we do not allow duplicate key values. So, this is again typical of database applications where the primary key is used for is used as the data in this for search operation or indexing operations, and the primary keys are normally unique. At every node the key must be greater than the left subtree, all the nodes in the left subtree, and the less than all the keys in the right subtree. This is a definition of the binary search tree. Now, let us look at how we search for a particular value. So, suppose we want to search for 0, 1, 3, 4, 2, 1, 9, this is the value we want to search for. Then we start with the root node and then we go to, it is greater, so we go this side, it is less, it goes here, and then it is less. So, we have found the value that we want to search for and the value identified. See, if you look here, what we did was we started with this, we found that this key which we want to search for is greater than 0, 1, 2, 3, 8, 4, 9, and so we went to the right. Then when we looked here and compared these two values, we found this was less, so we went to the left. Then we compared these two and we found that it was less, so we went here, and then we found the actual value. So, every time we are comparing the key value of the node we want to search for with the key value of the node at the node that we are searching for. Now, let us take another example 0, 1, 2, 0, 7, 3, 9. So, we compare that with this value and we find that it is less. So, we go to the left, you find it is greater. So, we come here and we have matched the node. So, the value has been identified. Now, let us search for another value. So, we want to search for this. So, we first compare it with the root and we find that it is greater. So, we come here, then we search with the next node, we find it is greater. So, you come here, we search for this and then we find that there is it is less than this, we have to go here, but there is no node here. So, at this point the search stops, saying that this value does not exist in this binary search tree. So, this is the right subtree and this is the right subtree of. So, if you take this node, all the nodes in this right subtree are greater than this node. If you take this node, all the nodes in the left subtree are less than this node and so on. Okay. Similarly, this side, if you look here, all the nodes here are less than this. So, this is a typical another way of looking at this. So, what we do here is, if you look at this 63, all the nodes to the right of 63 are greater than 63, or the nodes to the left of 63 less than 63. Now, if you take this part, if you take 41, all the nodes to the left is less than 41 and right is greater. So, if you go here you will find 34, 41, 56, if you go this side you will find 72, 89, 95 and so on. So, this is the typical way in which it is represented 3, 1, 0, 2, 0, 1, 2, 3, 4, 5, 6, that is the representation. Let us look at the implementation of the search algorithm. So, searching in the binary search tree, you want to search for a particular key. So, it implements a binary search based on comparison of the items in the tree. The items in the binary search tree must be comparable, that is you cannot compare nodes one integer with a string and say it is a binary search tree. So, all the nodes must be homogeneous, in other words. So, the search starts at the root, it probes down comparing the values in each node with the target till it finds the first item equal to the target and returns this item or null if it is not there. So, if the tree is empty, it will return null because you cannot find it. Else if the item in the node equals the target, return the node value. If the item in the node is greater than the target, then that means the target is less, so you have to search the left subtree. If the item in the node is smaller than the target, that means the target is in the right, so you have to search the right subtree. So, this is the code, this is the root of the tree where you have to access the tree, and this is the key value that you have to search for. So, it will return a pointer to the node that contains the key. If there is no such node, it will return null. So, if not root, that is there is no root, then you return null. If key is equal to root, the value of the key at the root, then return the root. If key is less than the value at the root, then return, you are recursively calling this search algorithm with the new root, which is the left subtree's root, and the same key value. So, if the key is less than the root, that means the key you want to search for is less than, then you have to search in the left. Otherwise, it means it is in the right. So, you return call search again with the address of the right subtree and the key. So, this is the right subtree. If it is greater, right subtree, if it is lesser, left subtree. So, now let us go into the next algorithm, which is the insertion into a binary search tree. Now, even when you are inserting, here the issue is that when you are doing an inserting, you have to search for a proper position in which to insert. So, actually the previous whatever we have discussed also comes here where we do a search for the proper position. So, let us look at how you construct a binary search tree. Now, this insertion is also used for constructing of a binary search tree, where you start with an empty tree and then you keep on inserting one by one the node. So, construction and insertion, you can insert into an already existing tree, or you can give a list of nodes with which to construct a binary search tree. So, now let us take this value and we want to insert this value into this tree. So, what we do is we start here and we know that this is less than the key here is less than the key here. So, we have to search this left subtree, that much we know. So, what we do, we call the search algorithm again, remember we have already discussed the search algorithm. See, we call the search algorithm with the address of this node as the new search algorithm, and we come here and we find that it is less than this, I am sorry, this is the node that we want to insert. So, this is more than this is more than this. So, you have to insert it here, but you find this is less. So, this is the position where this node has to be inserted, that is the first step you have to do, then you do the actual insertion. So, insert an element in a binary search tree involves creating a new node and then reorganizing the tree. The parent node link to you have to reorganize, and what you do is the parent nodes have to link to accommodate the new node. So, typically you will always insert into a terminal, you will always insert as a terminal node only, and we will never insert a node in the middle of a binary search tree. So, steps: if the tree is empty, then make the root node point to this node. If the tree contains nodes, then compare the data with nodes data and take appropriate path, basically left subtree or right subtree path, till a terminal node is reached, and then when a terminal node is reached, you look at what the key values and accordingly you attach it as the left or right subtree of a terminal node. If the data the node is less than the node's data, then take the left subtree, otherwise take the right subtree. When there is no more nodes, add the node to the appropriate place at the parent node. What I meant by appropriate place is either the left or the right. So, let us look at the method of insert key. So, what we are doing here is places a new item near the frontier of the BST. What do you mean by frontier is that the terminal nodes. So, while retaining the organization of the data. What is the organization of the data? Take every single node, the left subtree should have nodes that are less than the root and the right subtree should have nodes that are greater than the root. So, what you do, you start at the root, probe down the tree till it finds a node whose left or right pointer is empty and a logical place is found for the new node. Now, the insertion uses a binary search to locate the insertion point. This is what I said, that we do a search operation before an insertion to find the actual point where you have to insert, and it is based on the comparison between the new item and the values of nodes in the binary search tree, and elements in nodes must be comparable. As I already told you, if you have integers, everything should be homogeneous data should be available. So, let us take the first case. The case is the tree is empty, set the root to the new node and containing the item. So, now you are actually creating a binary search tree, otherwise the tree is not empty. You call a recursive algorithm to keep on searching for the actual place and putting it there. Now, let us start and discuss the example of a binary search tree. So, first we have to see whether we want to insert, okay, we have decided that we want to insert a node called 12 into the binary search tree. Now, first step that we have to do is we have to check whether the binary search tree is empty or not. As we have seen, we have already got the binary search tree here. So, we have to do a search for where to put this 12. Another condition we have to check is if we find that this 12 already exists in the binary search tree, then we do not allow for insertion, because we are not allowing duplicate nodes. So, we start with 12 and we check, we are given the root of the binary search tree. So, we check with 12 and the root and we find that 12 is greater than 7. So, we move to the right of the binary search tree, that is the right subtree. Then and the node, the root of the binary search tree that we want to search in now, or the right subtree, is 9. So, we check 12 with 9 and we find that 12 is greater. Again we have to move to the right. Now, this is the node of the right subtree we have to search now. We find that 12 is greater than 10. So, again we have to move to the right. Now, when we move to the right, we find that the right subtree is empty. So, this is a typical location where, and this is the location, we have found the actual insertion point, and this is the location where we want to insert the node 12. So, we insert it here, and for insertion purposes what we have to do, initially the link of this node would be set to 0, that is how we find that it does not have a right subtree. Now, this 12 has to be placed in a node, its right pointer and left pointer has to be made equal to null, and the right pointer of this 10, which we should have stored the location of, should now point to the new node. So, now we have a new node with 12 in this position. So, this is how we do the insertion into a binary search tree. We use the same algorithm for construction of a binary search tree also, where the nodes are given in a particular order and you keep on inserting by search, insert, search, insert till you come to the end of the list of nodes. So, let us look at the pseudocode for insertion. If the tree is empty, that is we do not have a tree at all, create a root node with a new key, that is it. Otherwise, you compare the key with the top node, not top node, root node. If the key is equal to the key of the node, then replace the node with the new value. Else, if key is greater than the node key, compare key with the right subtree. If subtree is empty, create a leaf node, add a key to the in the right subtree. Key is less than, compare with the left subtree. If the subtree is empty, create a leaf node and add the key to the left subtree. Now, please look here, this algorithm is actually a recursive part of the algorithm. This is also recursive. So, what happens if you compare the key with the right subtree and the right subtree is not empty, you go back here, okay, compare it with the root. If it is, if there exists a node, then you compare, otherwise you come here, go to the right and so on. So, you keep on recursively calling the insertion algorithm till you come to a point where you reach either an empty right subtree or an empty left subtree, and then you create a node and you do that. So, this up to this point we have seen a pseudocode of how to insert an element into a binary search tree. Now, we are going to see the actual code for inserting a node into a binary search tree. So, what we do here is insert pointer node. This is a pointer to the root of the tree where we want to do the insertion, and this is the key we want to search for. So, what we do is we put the pointer to point to this is the search algorithm. So, first we have to call the search algorithm. Remember, the search algorithm will return a node, the pointer to the node where you want to do an insertion. Actually, it will point to a node whose child has to be created and whose there we will search for the node. So, in this particular step we are calling the search algorithm, which we have discussed before the break. Now, if this is not a node, then you have to create a new node, and otherwise you have to say that you cannot create a node because the memory is full, you cannot do insertion. This is true for most insertions. whether it is an array. If it is a linked list, it is slightly different explanation of what we mean by a full that we have already discussed. Okay. Now you come here, now what you do is if that node's pointer has key value and the pointer to the node and that node's key value is equal to the key, then you put that left and right is equal to null, otherwise you go to the left, otherwise if it is less than, and if it is greater than go to the right and keep continuing to do this algorithm. So, what actually this algorithm does is you first search for a place, and if you have found the place you do the insertion. If you have not found the place, you go to the right subtree if the key is greater, and you go to the left subtree if the key is lesser. The order of, now here you may wonder, if I give you a list of keys that I want to insert. Remember, the keys can be as simple as integers, can be as strings, can be a complete record of a database with a primary key. So, keys can be anything, it can be a primary key value also. So, the order in which you give the data determines the shape of the binary search tree. So, create a binary search tree from the same set of data presented each time in a different order. So, I have given you here 3 sets which are ordered separately. Now, here I have 17, 4, 14, 19, 15, 7, 9, 3, 16, 10, and here I have given this in some other order. Here if you note, I have given it in decreasing order. Okay. So, now if I take this 17 and I want to create a tree, what I do? I first see that the tree is empty, binary search tree is empty, I create 17 as a root node. Then I take 4, okay, and I see that it is less than 17, so I attach it to the left side of 17. Then I see 14, 14 is less than 17, so I come here. Now 4, it is greater than 4, so it goes to the right of 4. 19 is greater than 17, so it goes here, and so on. Okay. Now if you take this, what happens? I have 19, now that is a root node, 17 comes this side, all these nodes will come only on the left. So, I will have a root with only left subtree and no right subtree at all. So, the construction or the shape of the binary search tree depends on the order in which you give the data points, but however please note that it will always have the property. The property is that take any node in a binary search tree, the key of the root and compare it to the key of the root, the left subtree will have all keys less than the root key at the root, and the right subtree will have all keys greater than the key of the root. The algorithm is perform search for the value x, search will end at node y if x is not in the tree. If x is less than y, insert new leaf as new left subtree for y. If x is greater than y, insert new leaf x as new right subtree of y. Now, this is the algorithm that we have already seen before, but the issue here is that we want to do a little analysis of this algorithm, because search operation is a very important operation in a lot of computer science applications, including databases, search engines and so on. A new application that has come out is search engines. As you know, there are a large number of data, and the keywords that you use for indexing also are available, and those keywords are actually stored in tree structures, not exactly this tree, but this is the fundamental of all of the trees that are later on have been used for databases and for search engine. Sees that if it is a balanced tree, then the order of log n is the time that it takes for, which is a very acceptable time for any operation that you perform on a balanced tree. But insertions may unbalance the tree, so that is another issue that we have to do later on. Okay. Now, let us take an example of insertion. Suppose I want to insert 20. So, what happens? 10 is less than 20, so I go to the 20 is greater than 10, so I go to the right. Then here I see that 20 is less than 30, so I go to the left. 20 is less than 25, so I have to go to the right. At this point I find that there is no left subtree, that is, this is a terminal node and it has no left subtree, and I know that I have to attach this 20 as a left subtree of 25. Okay. So, what I do here is that I create a node for 20, okay, make its left and right pointers to be equal to, here we are assuming that the tree is represented using a doubly linked list. So, you have a node with a left pointer pointing to the left subtree and the right pointer pointing to the right subtree. So, here as you know, before the insertion takes place, the left subtree and the right subtree would have been null. Okay, that is why you got that the left subtree is empty. Now, I want to insert. So, when I want to insert, first I have to create a node for this 20. Okay, and I make its left pointer and right pointer to be equal to null, because now this is the new terminal node. Now, in addition, I already know the address of this, which I have got from the malloc, that is the dynamic storage, and then I make the left pointer of this, the right pointer would have been null, I do not change that, I make the left pointer of this to point to the new node created. Now, I have created a binary search tree with 20 inserted into the binary search tree. If you note that 20 is less than 25 and but greater than 20, it follows all the rules of the binary search tree. Change the dynamic set represented by the binary search tree. You have to ensure that the binary search tree property holds. Basically, we are looking that the binary search tree property has to be catered to every time you do a change, whether it is insertion or deletion. Here we have, up to this point in this lecture, we have looked at only insertion. Deletion is much more challenging task, which we will see in the next lecture, and every time you do either an insertion or a deletion, we have to ensure that the binary search tree property is maintained, and that is the challenge that we have. In insertion, how did we do that? We searched for a point where we have to insert, and then and we kept on searching till we came to a point where it was possible to insert, because the node that we reached was a terminal node, and then we did the insertion. So, that means we ensured that we searched for a point where if you do the insertion the property of the binary search tree is maintained, but insertion is easier than deletion. So, let us look at this algorithm a little more in detail. So, you have a pointer to t and then you have z, which is the node that you want to insert. Okay. Now, let us look at the pseudocode for insertion. Actually, these points are not meant only for insertion, it is meant for insertion and deletion. Now, basically when we are doing insertion or deletion, what we are doing is we are trying to change the binary search tree. Now, when we try to change a binary search tree, the condition is that we have to ensure under no circumstances should this binary search tree property be violated. Okay. So, after the change also the binary search property should be should hold. So, and whether we do an insertion or a deletion, the property has to still be maintained. That is what we have to do, and that is a challenge. Now, we will talk about the insertion. How did we ensure that this property was held even when we do insertion? What we did was we searched for a proper place in which to do the insertion, and only after we found such a place did we do the insertion, and we found a place such that it was a terminal node and we knew whether to attach it to the left or the right, and so we ensured that by searching for the proper point at which to do the insertion, we ensured that the binary search tree property still holds good even after the insertion. This is easier to do in the insertion because it involved a search only, while in deletion it is a more challenging job. So, again let us go to the tree insert algorithm. So, this is the root pointer to the root, and this is the z is the node the key value. Okay. So, y is equal to nil, the pointer, x is the pointing to the root of the tree. While there exists, that is while the tree exists, what you do is you put y equal to x, and if the key value of z is less than the key value of x, note that x is the the root node in the first call, then make x to be the left of x, that is key value is less than the root. So, you have to go to the left. Now, you are going to do the whole algorithm with x pointing to the left subtree. Otherwise, if the key value is greater than the root value, then you go to the right. Okay. So, now you have x pointing to left or right, then p of z you make equal to y, if y you do this while x is not equal to null. Now, if y is equal to null, then root of t is equal to z, that is this is the case where you are going to insert when the root has to be inserted. So, that is what you do here. So, what you are doing is left of y is equal to z and right of y is equal to z and so on. So, this is the algorithm that you have for insertion. This is the insertion again. So, this is what you will happen. Now, suppose I want to insert a node, I start from here. I think we have discussed this in detail. You must know how to insert the node. Now, let us look at the analysis of insertion. So, initialization is just a constant time, while the loops into 3 to 7, that is here 3 to 7, here we are doing the search. Okay. So, a place to insert z, maintaining the parent y, that is very important. If you note here, we have maintained the value of the parent, because when we find a place we want to know, change the parent's left pointer or right pointer, which we have discussed before. So, that is maintained. So, this takes about 0 h time. What is this h? H is the height of the tree, and lines 8 to 13 where we do the actual insertion, that takes only constant time. So, the total is 0 order of h time to insert a node. So, insertion algorithm is fairly not a very costly operation. So, the method used to search a binary search tree was discussed, and we also use the search algorithm to find a position in which to insert, and then we did the actual insertion process. Actually, the time for the algorithm was basically the searching time only. The insertion is only a constant, it takes only a constant time, because you have to just insert a node. Okay. So, that is as far as the binary search tree is concerned. Now, let us take a small problem. Assume that you are given a binary search tree. Okay. First, we will have to trace the path. I want you to trace the path that you will follow to search for the binary, any node in the binary search tree. As an example, suppose you have this particular node. Suppose I ask you to search for 28. This is not the tree that is given, but if you want to search for 28, you have to go to 56, 26, 28. That is the path. So, do the same for the given tree. Okay. And then suppose the node is not present, that also you should be able to trace and tell. Next, I have given you a problem where you have to insert the nodes 28, 9, 85, 23, 54 in that order into the binary search tree, and in the binary search tree that has been given in question 1. Okay. So, do these problems, you will understand what you mean by binary search, search in a binary search tree and insertion into a binary search tree. So, I hope you have understood what we are trying to do by search and insert, and thank you very much.